Okay, so let us begin. As Prashka mentioned, my name is and I will give tutorial on using DESDEO to solve a real world data driven problem. Um, okay, so just as a brief overview, I will introduce the problem in a very brief manner so that you don't know what I'm talking about in these slides. And then we'll follow a natural problem solving process. We'll start from the data and I will talk more about what the data contains, some problems that arise because of the way the data is presented, how we solve those challenges, and then I will go on to the following steps, talk about the problems that are faced during all of those steps and how we solve those problems. And then I will talk about, during all of these steps, I will talk about how we use DESDEO to make solving these challenges or even possible in the first place. So before I talk about the problem, who am I? I am a postdoctoral researcher here at multi-objective optimization group. I've been here for the past 5 or so years. I started out as a doctoral student, and my interests are mostly in multi-objective evolutionary algorithms, interactive methods, surrogate modeling, visualization aspects, most of which will see somewhere during the course of this particular tutorial. So about the problem, let's do some role play. Let's imagine that you are some engineer in some company that is trying to build a ship. You have to make lots of decisions, but today your job is simple. You have to make just one decision. What should the hull of the ship be made out of? Probably some metal, and some kind of steel probably. But if you go to market, you can find many different kinds of steels with slightly different compositions or slightly different ways of manufacturing the steels, which give it different properties. So it's a very important decision that you have to make. And you have to make sure that the properties of the steel are good enough for the application. Because you are an expert in this field, you know that this particular these kinds of materials can have certain behaviors in normal temperatures and entirely different behaviors in cold temperatures. And because the ship is going through, I don't know, the Arctic Circle, perhaps, it is very important to have good values of these properties, both in the normal temperature and in the cold temperature. Because at the end of the day, you want to avoid this. So what are these properties that should be good or good enough? What is performance? In material science, there are many different kinds of testings you can do, and these tests can result in many different properties that tell you whether a material is good enough for a certain application. For example, here I'm showing the results so-called tension test. You just take a material and try to pull it apart. And on the axis, you basically plot the force that you're trying to apply to pull it apart and how much it is stretching. Strain is how much it is stretching, stress is how much force you're applying. And material behaves in a spring-like fashion for a certain part of this, certain amount of stress. And if you pull it, it will spring back to its original dimensions. So the higher this yield strength is, which is basically the level of the stress, the better, because if you apply a large amount of force, if it springs back, it's good. But beyond that level, it starts permanently deforming. And if it starts permanently deforming, there's a good chance that your ship might start sinking at that point. The other important aspect is this ultimate strength, which even though it starts deforming, doesn't mean that it will break. It will break after this point, however. But this is also important. Let's say you hit an iceberg. If the stress goes beyond this, there will be a hole in your shell. So that is also something that is important to have a high enough value. There are some other tests. For example, this is a fun test called a Charpy impact test. You take a piece of material and then you basically let it run. Videos are not running. It's running.
The charpiness of materials.
Okay, so basically, you take a piece of material, the metal that you want to test, and you basically throw a hammer at it. And you basically measure the height at which the hammer started and the height at which the hammer ended up. And the difference is basically the difference, the energy it took to break the material apart. And you can measure this at different temperatures, like you measure this at normal temperature, then you put the material in liquid nitrogen and then measure it again. And you can basically test how much energy it takes to break a material at different temperatures. So this is also something good to measure at various temperatures, and because we are running at the Arctic Circle, at sub-zero temperatures as well. And there are quite a lot of other tests that you can do. You can measure fracture toughness, how easy it is or how difficult it is to fracture, how hard a material is. Like you might know that diamond is one of the hardest substances. So you can measure hardness, you can measure fatigue resistance. Like if you keep cyclically doing some action with the material, like in a car engine, it works in a cycle. So you can have some fatigue over time, and the ability to resist it. It's also good. Corrosion resistance is a problem. Many different tests that you can do. So as the engineer who is making this decision today, all of these things can be very important for you. But unfortunately, there is not an easy way to predict any of these properties based on, for example, the composition of a material. What you can do is actually create that material and then do these tests, which can be expensive. However, steels are something that we have had for a very long time. So other people have created many different kinds of steels and done many of these tests, maybe not all of these tests for all possible compositions, but some of these tests have been done for a large number of different kinds of steels. So now that we have a basic understanding of the problem, this is the structure that I will follow throughout the presentation. I will talk about the data that we have, the experiments that have been done in the past, and how we can use that data to help this engineer choose a composition of steel for their particular application. We'll talk about some surrogate modeling aspects. I will talk more about what that is a bit later. We'll talk about how we did multi-objective optimization and decision making as well data about in the presentation. So what is the data that we have? This is just a screenshot of Excel sheet. Not much to see here at all, but I would like to point out that maybe you can see there is a lot of red here and a lot of empty space here. It will become important later on. What is this data? This data has been made by someone by collecting basically 1 or 2 data points from published research, maybe over the past 5 or 6 decades. Maybe they read a paper where someone had created 1 or 2 of these compositions and done some number of tests. And they basically compiled this over a period of time. But this data set itself has no connection to multi-objective optimization at all. It's just a bunch of researchers conducting some tests. One important thing is that these tests were done by completely different research teams with completely different materials, completely different tools over a very large amount of time. So there can be a lot of what we might call noise in the data. Moreover, they don't all measure the same things. The researchers measured whatever they found important for their particular application. So all of the tests that I mentioned, maybe the researchers only conducted 2 or 3 of them and measured those few properties for that particular composition of the material. But in general, the data set contains, on the left-hand side of the data, we have the chemical composition of an alloy of steel. So how much carbon does it have? How much nickel does it have? How much molybdenum does it have? And so on and so forth. And on the right-hand side of the data set, we have some physical property. Maybe it's the yield strength that I talked about earlier, the ultimate strength, or maybe some other property. Or maybe multiple properties. So this is what the left-hand side of the data set look like, which measures the chemical composition. Let me write this. So we have the chemical composition, and as I mentioned, there are many different papers from which this data set was collected. So they considered many different kinds of alloys. What this means for us is that some paper might consider the effect of adding nickel to a composition of steel. So they might have some value of nickel, but the others do not care about nickel at all. So they might not have nickel at all. So that is why I was pointing out the amount of red in the left-hand side of the data set. Most of the values are 0 here. I put the zeros there. Most of the values were empty originally. But in total, there are about 20 alloy elements across all of the data points, most of which have a value of 0. In some small number of cases, we have some non-standard values as well, like a range, which can be problematic. So we had to fix those values one at a time, basically. And the right-hand side measures the physical properties. About 30 different physical properties in total, but most of the values are empty. So it's not directly useful. There are about 750-ish rows in the whole sheet in total, but that does not mean that we have 750 data points here. For some of these objectives, if we are calling these objectives right now, we might only have 10 data points, which makes it very difficult for us to use that as an objective in the multi-objective optimization problem. So it's not as simple as just having these 30 columns as objectives right now. We need to do something to extract as much information as we want from this data set. So we have to clean the data. First of all the empty columns need to be dealt with. All the weird ranges need to be dealt with. And we need to choose which columns to use for future steps as well. Not just on the right-hand side of the objective side of the data, but also the decision variable side of things. So how did we treat empty cells? Do we treat them as 0? Do we delete the entire row? It depends. On the left-hand side of the data, I mentioned, for example, the example of nickel. Some teams might be interested in nickel, but not. So if a value is empty, it is reasonable to assume that they just did not add nickel to the material. So we can treat that value as 0. But if a physical property is empty, that does not mean that it's 0. It just means that they did not measure it. So we need to apply different strategies depending upon which cell is empty. Some of them we can treat as 0. The others, we just can't use that particular row at all for that particular column. How do we treat cells with non-standard values? We can do some case-by-case intervention. If it's a range, maybe it's reasonable to take the middle value of the range if the range is small enough. But it's something that we need to discuss with the decision makers. So you are the decision makers, you can decide what is a reasonable way to deal with these non-standard values. As for which columns to use, But I'll come back to it later. But the tools used up until this point, well, I used Microsoft Excel for the screenshots, but the other tools that I've used, Python and Pandas up until now, just to load the data and do some kind of pre-processing. The non-standard values, the empty cells, all of those things can be done with Pandas pretty easy. If you know what to do, Pandas are the way to do it. As for formulating the problem, I mentioned that we had about 750 rows, out of which only 3 of them, I think, had enough non-empty cells for the physical properties that we can actually train surrogate models based on that particular, based on those values. So we can extract at least 60 objectives out of this data. We started out with 30 physical properties, but ended up at 3. Yes.
How do you find it's accurate enough with these 3?
Well, the other ones only had maybe 10 or so dimensions. At which point, if we have like 20 decision variables, input space has 20 dimensions and only 10 data points, we can reasonably conclude that we won't be able to train good enough surrogate models at that point.
And you did some feature engineering to decide about this?
Not a lot. We'll come to it in a few slides, but this is just me making some initial decisions based on just some experience. We'll do some more thorough analysis a bit later. Yes.
How many non-empty columns were rows in the 3 columns?
I think about 500 for 2 of them and about 400 for the third one. 400 to 500. But this does not mean that we can just straight up use these 3 columns as objective, because if you think about the 20-dimensional input space, what I found was all of these measurements were done in totally independent regions of this 20-dimensional input space. So even if we were able to train very accurate surrogate models, if we took any particular point in this input space and tried to evaluate all 3 objectives, at least one of these models would be extrapolating rather than interpolating, which can be bad. That is something that can be problematic if we are doing multi-objective optimization as well. It would be preferable if these 3 properties were measured in the same region of the space, so that the models, we would know that they are at least somewhat accurate rather than just wildly predicting some values. So how can we get around this issue? And is there a way to somehow add even more objectives? Some way to extract even more information from the data? Because this is all the data that we have. We do not have the ability to, the time or the money to create new compositions and test them again, and to form a new data set specifically for multi-objective optimization. This is all we have. So extracting as much information as we want would be, as we can, would be very useful. So one way to deal with this issue is to not deal with this 20-dimensional input space in the first place. As I mentioned earlier, for many of these teams, they only considered a small number of these alloying elements. So if we are able to reduce the number of dimensions, maybe more and more of these data points, these samples that have been measured, they will start overlapping, perhaps. So I did a bunch of tests to find out which of these alloying elements are important to some of these objectives. For example, let's imagine that all of these tests have been done for the yield strength of the material. According to a bunch of tests like CA or the calculating the F value or this mutual importance, all of these tests, by the way. You can find out more details about this in the scikit-learn documentation. All of these tests, I use the scikit-learn package to do all of them. But basically, they can tell us whether a certain input, a variable, this case, decision variable, allowing element was important to a certain objective. And based on a bunch of tests, we see that cerium or vanadium and carbon seem to be very important, but calcium, zirconium, or oxygen are not as important. So at least for that particular objective, we can remove a bunch of these decision variables entirely from consideration. And suddenly we are not dealing with a 20-dimensional input space, we are dealing with, let's say, 10 or 13 or 15 dimensions, depending upon which of them. And we can do this independently for every other objective. Maybe phosphorus is important for the yield strength, but we can do the same calculations for ultimate tensile strength, and maybe phosphorus won't be as important. So now we don't just have one set of decision variables, but we have one set of decision variables for one objective, another set of decision variables for another objective, and each one of those sets is smaller than 20. Number of dimensions is smaller than 20. And if phosphorus is important for one but not for the other, the optimizer, whatever value of phosphorus it decides to give, it can be sent to the object that considers it important, but that value can be ignored for the other object. So that is another way to have more overlap between all of these measurements of all of these objectives. This is us basically trying to make sure that the samples have an overlapping region so that we are interpolating rather than extrapolating these values from the models, which will create data. Yes.
Did I get it correctly? This heat map analysis can be done for each objective.
Yes, each objective independently. What about more objectives? I mentioned that for most of the other objectives, there are very few, less than 50 data points for each in each of the columns. But that does not mean that we cannot use them. A lot of research have been done about these the experimental techniques that I showcased in the beginning of the slides, and many researchers have tried to predict one of the properties based on value of the other properties. So perhaps we can combine data from the rest 27 of these columns to get at least 2 or 3 more properties. And that is what we did for that is what we did. I have not mentioned it here, but the Sharpie impact test, the one with the hammer that I talked about, there were about 20 or so columns that were only dedicated to those kinds of tests, but they were just done at a different temperature. And once you know it at maybe 2 or 3 temperatures, you can basically predict what value it would take at any given temperature within a certain range. So we combined 20 of those columns together, form a single objective for the Sharpie energy value at a certain temperature that the decision makers thought was important for this particular application. So we have one additional objective based on data from 20 different columns combined. And we thought, okay, we don't have to limit ourselves to this particular data set. There are things that we can get from the wider internet as well. For example, it is trivial to find the cost of ASR elements. If you want to put carbon in your steel, it would be very cheap to use. If you want to put vanadium in your steel, it will be very expensive. So this can be a naive way to calculate the cost of the material. Obviously, there are many other things involved in a cost, but this can be a simple way to calculate at least the cost of the materials itself. And moreover, we have the values of the decision variables, like the optimizer sets some value of the decision variables, and the decision makers told us that just based on those values, they have a very simple linear function which can predict one more additional physical property. It's not very accurate, but it seems to work for the composition of steels that they were interested in. So we added yet another physical property based on just the linear combination of the decision variables. So we have objectives that come from data. We have objectives that come from the cost that we just got from the internet. And we have an objective that is just a linear combination of the decision variables. 6 objectives in total. So the objectives that come from the data itself, we need to form basically surrogate models here so that we don't use the data directly, we train models on them, and then the optimizer can ask the model what would be the objective value for a certain value of the decision variables. And the surrogate model can predict that, oh, it will have this value for this objective and that value for that objective. And based on that information, the optimizer can then conduct optimization. But there are hundreds of different surrogate modeling techniques that are openly available. Which one to use? What is the best one for our problem? Well, there are many different ways in which we can choose the best one. We just trained 10 or so, I think, different surrogate modeling techniques. All of these, again, are available either through scikit-learn or in the case of some of them, for example, XGBoost, there are some external packages from which we can get these surrogate modeling algorithms. But based on that, we basically did k-fold cross-validation. If you are aware of cross-validation, if not, again, you can look at the scikit-learn documentation. They have very good documentation on these kinds of tests. But basically, we trained a bunch of circuit models on all of the 4 objectives that is based on the data, and we measured how good that particular surrogate model was for that particular objective. So this EXTR, which is extremely randomized trees, seems to be the best one for yield strength, but this XGBoost based model seems to be the best for UTS, and so on and so forth. So based on these tests, we have a choice for each one of these surrogate models. Again, we are not using the same surrogate model for all 4 objectives. We have 4 different, I think 3 different surrogate modeling techniques across these 4 objectives. So 3 different surrogate modeling techniques, 4 models in total, but and 2 more objectives aside from that. So up until this point, are there any questions? Okay, carrying on. Let's say that you have done all of the management of the data, the cleaning of the data, and you have trained your surrogate models as well. For example, by using scikit-learn and done all of these tests, and you now have everything you need. Start formulating your problem. How do you do it in DESDEO? As you mentioned, we have this data problem class where things are very simple. There is no boilerplate needed. You can just give it the data set directly, tell it that, okay, these are the names of the objectives or the decision variables. It will find those decision variables and objectives in the data set and create this data problem class for us. And it also has this train method, which can accept surrogate modeling techniques from scikit-learn. So you can train surrogate models using data problem class very quickly and very easily without a lot of code. And it even has support for different kinds of surrogate modeling techniques for different objectives or different setting different hyperparameter values for different objectives if needed. Unfortunately for us, it makes the assumption that all of the values for all of the objectives, all of the decision variables lie in a single data set. This is a problem for us because when we did that analysis of which decision variables what objectives, we had to break the data set into because not only do we have different ranges for different decision variables, we also have now different sets of decision variables. So even the sets are not the same. So we cannot directly use data problem class, but we have something to fall back on, the default demo problem class. We can simply use that. If we do this, then we have to do all of the hard work ourselves. We have to train our models ourselves and pass it to DESDEO. But it is easy enough to do. Here I have a simple example of how to do that. It's not actual code. This will not run because this assumes some things. For example, it assumes that we have some kind of surrogate model called problem model, which can accept 4 data sets or 4 different objectives and train it. But you can imagine that there is some code inside it which does all of that. But once you have those models trained, we can do the same thing as usual showed. We can build our variables, we can get the variable names and lower bounds from this particular model. Imagine that there is some code inside the model to do that. We can form the objectives where the evaluator will take the model.predict function. In this case, the model.predict does not just predict the 4 objectives from the surrogate model, but also the 2 other objectives, linear combination and the other, the cost one. All of that code, imagine that it's just in this predict function. So a lot of things are happening, but in theory, on the DESDEO side of things, you can simply do it this way. There is a lot of mess inside this model class, but we don't need to worry about that. Once you have variables and objectives, you can simply just use the MO problem class as user showed earlier. And that's it. We now have the problem formulation. All of the mess, we have this. Yeah.
Sorry, could you please explain more about the model train function and the evaluator model predict?
So the evaluator is just a Python function which can take decision variables as the input and give objectives as the output. This class is a vector objective class, so it assumes that this evaluator will return multiple objectives at the same time. Not just one objective, but maybe 3, 4, or in this case, all 6 objectives at the same time. So it will this evaluator method, should be able to take the decision variables as input and return all of the objectives as output at the same time. Inside this predict method, what is actually happening is we have 4 different surrogate models for our 4 different objectives. And if you're familiar with scikit-learn, we have in the surrogate models, they have their own predict functions. So we are calling the predict function of those 4 surrogate models inside this function, collecting all of the results. We are calculating the linear objective and cost objective and collecting all of that information, combining it into a NumPy array, and then returning it. That is all that is happening in this particular method. And similarly for the train method, all that is happening here is that we are training 4 different surrogate models in there. You can do that however you want. There is no return happening here. We're just saving those 4 surrogate models inside this model variable. Does that answer your question?
I'm still a bit confused about the train. Sorry, I didn't quite get it. So,
Pattern is just this. This evaluation.
I mean the model train.
It just. Are you familiar with scikit-learn?
Sorry.
Are you familiar with scikit-learn?
Not really. So I'm new to this field. Sorry.
Okay, so basically that is not related to DESDEO at all. It's a very popular machine learning package. If you're familiar with Python, scikit-learn is one of the things that you should look into. And the format that they follow is surrogate models have this train method that can accept data and just they have the fit method, if I remember correctly.
Oh, I got it.
Yeah. So there is a fit, there are 4 different fit calls for these 4 objectives happening inside the train method. That's basically all that is happening.
Yeah, no.
I assume your decision variables is the composition of the material, so they have to add up to one.
Yes. We are ignoring, so in the composition of the material, we are ignoring the amount of iron. Because it's steel, iron is just assumed to be there. For all of the other ones, the lower bounds and upper bounds are such that the sum will always be less than 1. So whatever is left over, we can assume that we have that much amount of iron in the material. In fact, the category of steels that we are considering here is called microalloy steels. So they're not just lower than 1, they're very, very small. It's mostly iron, like more than 95%. Any other question?
So where do you define the surrogate models? Is it in this YS?
In this model.train call. So all of these experiments have been done before we started modeling the problem in the first place. At this point, we knew that, okay, we will need this EXTR model, we will need this XGBoost model, we'll need that's also, I think, no, flat boost. So we'll need these modeling algorithms. So when I was creating this problem model class, I made sure that this first data set will be used with this EXTR, the second data set will be used with this XGBoost, and so on and so forth. So inside this problem model itself, I have basically hard coded that this data set should be used with this circuit model, that data set should.
And then you take this surrogate model from this data, or
These circuit models are implemented within scikit-learn or some other packages. I will mention those packages later. But we don't need to implement these things. They have already been implemented, so we just reuse them. Any other question? Right? So at this point, we have 6 objectives, 4 of which with these star bugs are coming from the data, and we are training some circuit model. This chart hierarchy actually came from combining multiple columns to form a single objective. So complicated. And then we have 2 other objectives that is based on some combination, linear combination for this one, and this is just material cost which we got from the internet, and that is also a linear combination. Like the amount of material multiplied by the cost of the material. And we have these 6 objectives, but oh no, you're not alone. There are 2 different decision makers here, which can have some additional issues. DESDEO, even though it was developed with interactive multi-objective optimization in mind, but originally assumed that we would get preferences one at a time. There would only be one preference for one iteration. But if you have 2 decision makers, they might want to get 2 different preferences at the same time. We need to deal with that eventually, but for now, let's just keep it at the back of our mind. But we have these 6 objectives, and we have some evolutionary algorithms in DESDEO. So let's just try to, let's ignore that. The tools that I talked about, SciP for all the feature importance tests that we saw, scikit-learn for circuit models, XGBoost for the XGBoost circuit model, and GPM for another circuit model that we tested, but we did not use later on. All of these are Python packages. You can find them very easily, install them using pip. These are pretty popular, and they have pretty good documentation as well. Also open source. Most of these tools will be open source, except the first one, which is just used for screenshots. But yes, we have the 6 objectives. We can use some evolutionary algorithm from DESDEO to optimize all those 6 objectives at the same time without involving the decision maker, at least for this step. Just to see what kind of results do we get. Well, we get this mess. We have 6 objectives plotted in a parallel coordinate plot. We have maybe a few thousand solutions represented here. I don't know if you're familiar with parallel coordinate plots. Maybe it would be easier for you to analyze this over some time. The visualization itself that we used is actually interactive, not in the way of interactive methods, but interactive as in you can use your mouse to brush, filter, and those kinds of tools. So if you're familiar with a parallel coordinate plot kind of visualization, with some time you can analyze these solutions and maybe choose one of them. Maybe. I don't think so, but there are too many solutions here, if in my opinion. But for our decision makers, this is not a good way to show them solutions. They were not familiar with this kind of visualization, at least one of the decision makers was not. So this was not a useful for choosing at least the final solution for them. It's useful to know these ranges at least so that they can start forming their preferences. But the individual solutions themselves not as useful. So what can we do? We have basically an approximate set of very optimal solutions. They're not very optimal. We used evolutionary algorithm, yeah, but they're close enough. Maybe we can use some interactive method that can feed these solutions as a starting point, just so we can have a very quick interactive session. No need to calculate, no need to do any optimization, just use some interactive method to help us find some preferred solution out of this. So one of the methods that we have in DESDEO is called Nautilus Navigator. And the way Nautilus Navigator works is similar to what Giovanni showed earlier in the first tutorial about eNautilus, if I remember correctly. Yeah, we begin at a nadir point. And in this case, the video is showing a problem with 3 objectives in this particular case. And the ideology between Nautilus Navigator is starting at the ideal point, the nadir point, my mistake, and visualizing basically what region of the Pareto optimal, the Pareto front is reachable to you. If you are at the nadir point, you can basically reach any part of the Pareto front. And that is represented as a shaded region in this plot, which goes from the maximum possible value to the minimum possible value. If you see that the region shaded, you can eventually reach it if you go closer and closer to the front. And then the decision maker can decide how to go closer to the front. They basically imagine they're in a submarine and they can decide which direction to go in by giving these aspiration levels. So for each objective, they can decide which value they want to reach eventually. Which here they are shown with this dotted line. In the interface, they can drag this line up and down, or they can provide a certain value within this text box to give accurate values. So eventually, what happens in Nautilus Navigator is the point of view, which started at the nadir point, it keeps going closer and closer and closer towards the front slowly. The direction that it chooses to go in is defined by the decision maker. And the closer we go, this region that is still reachable becomes narrower and narrower. By reachable, we just mean which parts of the Pareto still dominate this point of where our submarine is. So the closer we go, the smaller the reachable region becomes. And eventually, if our decision makers have chosen these direction of improvement according to their preferences, hopefully we'll reach a point in the Pareto front that is preferred to them. Here we just saw a decision maker stop the process and move this direction of improvement. So they can change the direction of improvement whenever they want. If they don't like how these ranges are shrinking, and if they're afraid that they might not get the point that they want, they might try to change this direction of improvement. And if they think that, oh no, I've gone too far, they can also just take a step back and then give new directions. But eventually, at the end of the navigation process, this range shrinks down to a single point, which is a point on the operator front. In this particular case, no new function evaluations are happening at any point. We can start with, for example, the front that I showed earlier. This one, provided to Nautilus Navigator as a CSV file, for example, we have a user interface where we can just give an approximate Pareto front as a CSV file, and it will create a user interface which a decision maker can use to choose the most preferred solution for them out of the set of the points that have been pre-calculated. For this particular problem, however, this particular method was not as usable by the decision makers. First of all, there are two of them. This method only accepts one preference, the aspiration levels. There are other kinds of preferences this can accept, for example, bounds. Readers of that, but first of all, the two decision makers needed to come to a consensus, and then we still don't know whether these solutions are actually very optimal or not. So, not as useful for our particular problem. We tried it, but we found that it was not as useful. So, let's use some other method. There is something there. Let's go away. So, DESDEO did not have any method to deal with multiple decision makers at the same time, but we have quite a lot of methods, and we thought of a new algorithm which we could very quickly implement within DESDEO using the tools that we already had. We called that particular algorithm multidm/IOPS. It's a variant of the IOPS algorithm. If you want details of that, it's here. But in a very basic example, the IOPS algorithm tries to not do optimization in the objective space, but instead it forms a whole new space, which we call the preference incorporated space, where preference information is encoded within the space itself. And once you do optimization within that space and then map it back to the objective space, we find that all of the solutions that are found are very optimal and follow the preferences of the decision maker. And it was very easy for us to create the space such that it takes preference not from a single decision maker, but from multiple decision makers at the same time. And all of the preferences are incorporated directly in this particular space. And then we can do optimization in any way we want. We can, for example, even use the evolutionary algorithm that does not consider any preferences, but because the preferences are directly encoded within the space, whatever result we get out of it, if the evolutionary algorithm, it's approximately very optimal, but it will follow the preferences of the decision maker as well. And in our case, because we have multiple decision makers, it will follow the preferences of all the decision makers. One good thing about this algorithm is that because we are creating the space ourselves, we have a lot of control over this particular space. And if you're interested, there is another talk in the afternoon where I go into more detail about how this works. But for now, the important thing is that in this particular variant of the algorithm, the number of dimensions of the space in which we optimize is the same as the number of decision makers. So suddenly our problem becomes two-dimensional because we have to decision makers, even though in the background we have 6 objectives which we are optimizing at the same time. And how did we implement this particular algorithm? This is basically it. This is the entirety of the algorithm that we had to implement. This does not mean that the algorithm is very small. In fact, there is not a lot of logic here at all. Basically, this algorithm is so similar to many of the things that we already had in DESDEO that all we had to do is just do this and put it in DESDEO. It took everything else from DESDEO. For example, it utilizes skill realization functions, which we already have in DESDEO. It uses evolutionary algorithm, which we already have in DESDEO. It uses preference handling tools. So how do you get preferences from the decision maker? How do you handle those preferences? You already have it in DESDEO. And it uses the base IFS algorithm, which we also have in DESDEO. So all we needed to do was to implement this and then use all of the other things that we already had, mash them all together. And in 10 lines of code, we have a whole new algorithm, which can handle multiple decision makers, which was new to DESDEO. So we only need to implement the new and novel parts. In this case, the new and novel part is just we have as many skill realization functions in this case as the number of decision makers. That's it. Everything else comes from all of the things that were already in DESDEO. Again, more details about this algorithm, I will talk about it later in the afternoon. But for now, what I want to point out is it's actually pretty easy to implement new algorithms. If your algorithm has things like common properties with some other algorithm, there are chances that those parts are already in DESDEO. Just take those parts and use them rather than trying to reinvent the wheel. And now that we have this, I won't go into too much detail of what actually happened in interactive optimization, but the decision makers, even though they themselves were not very familiar with interactive optimization, they liked how they could give their own preferences. They tried it out for a few iterations and eventually ended up at a compromise solution as well. So the two decision makers arrived at a single solution both liked. And one thing that we found out later on when we were analyzing these solutions was that in every single iteration, all of the solutions that we found dominated the solutions that we found from the a posterior this one. So all of the solutions that we found through interactive optimization were better than solutions from this particular set. And that is not unexpected. Interactive algorithms here, we are only focusing on a smaller, much smaller region of objective space. And in this particular case, even though the problem is 6-dimensional, the optimizer, the evolutionary algorithm only saw 2 dimensions. So it was a much easier problem to solve for the evolutionary algorithm. And for us, that meant that we were able to find much better solutions much faster. And within less than a second, we were able to put the preferences into the method and get the results out and visual interpretation. So everything was pretty quick, and the decision makers were happy with the solutions. And we got pretty good solutions. And at this point, we have finally used DESDEO. So I can mention it in the tools first. And for the visualizations, we used Plotly. It's a very good tool for interactive visualizations with mouse to manipulate the visualization. So that was pretty good. Any questions at this point?
Another question.
Yeah.
Have you looked into catalogs of steel mills or data? They offer some catalog from catalog material.
Yeah, if they offer it, we can. Otherwise, we would have to pay money to get that particular data, I suppose.
So no, they sell it.
Yeah.
So if they want to sell it, then they have to offer specification.
In this particular project, one of our goals was to be as open as possible, use open source tools, use open data that is openly available. So every single tool and data that we have used here, you can actually find it openly now. So that was one of our goals. But yes, what you said is also possible. It's just that someone would need to pay for that particular, for that data, or we would need to collaborate with those steel mills. Right, that's definitely possible. Yes.
I assume the objective values that you report back to the user are the estimated values. So
Yes.
there's obviously a risk that your model is too optimistic and actually you can't reach these objectives. Have you checked that? Have you thought about how to feedback maybe the risk to the user, because the model may be more confident about some solutions than others?
Yeah, that is one of the things that I skipped over because of time, but when we were choosing these models in the first place, we did not just do this k-fold cross validation thing. We did a bunch of other tests as well. And once we had these models chosen, they were validated by those two decision makers as well. So we did a bunch of tests that basically we tried to find out what was the relationship between the decision variables and the predicted outcome. And if that relationship was what was in the literature as well, then we were more confident about these models. So if the model said that yield strength should go higher if we add more carbon, and the literature we saw the same pattern, then we have more confidence in this particular data set. At the end, once we had chosen a solution, if we had the budget, it would have been good to be able to actually do a real physical experiment by creating that particular composition of steel and doing the experiments, but we didn't have the budget. But yes, that's definitely a valid concern. Yes.
But if I got it correctly, basically at the very end, or in the middle, depending on you want, you could try to find the steel, the real steel, but you have only a few hundred of them, which correspond to this, your suggestion. Because it might be that you don't have such steel.
It might be, yes.
So, and then you could choose the existing steels and say decision makers, look, choose one of those 5, and basically, but you will never get this because of you don't have this.
Yeah, and in the post analysis, we did that as well. If I think I mentioned the paper in one of the beginning slides. In the paper, we have done the analysis to find out which one of these solutions correspond to actual real composition of steel. And we found, at least in this small set, we found like 10 or so different compositions that do actually exist. Yeah.
Yes, I'm thinking about the parallel plot going to Nautilus. You have a set of solutions, non-dominated solutions. So you can just use this set and apply Nautilus on that set. Is that
Yes.
correct?
We can also use real functions and actually do optimization while that is happening. But just pre-generating the set point of view of that issue. But at that point, we don't need to do any optimization.
I have a question related to this surrogate models and simulated data. So if you have simulated data, does there always need the surrogate models in the DESDEO with continuous variables to choose from?
Not necessarily. There are certain methods where instead of trying to predict certain values, we just take the data and try to find the closest point. Okay. There are some methods that do. Okay, we are running out of time, so I will very quickly end this talk. The outcome, we were able to extract a lot of information from the data. We only used open source tools and open data and implemented a whole new algorithm pretty easily. And the DMs themselves conducted interactive optimization for the first time, and they were pretty happy. And that should not be the last slide. There should be a thank you slide, but thank you.